Hello dear students. In the previous section, you people have discussed about magnetic Lorentz force. When a charged particle happens to move in a uniform magnetic field, then the charged particle will be experiencing a force because of which it describes a circular path if it enters the magnetic field in a perpendicular direction. If the magnetic field is acting in the upward direction, and if a charged particle q is moving with a velocity v, then as it enters into the uniform magnetic field, it experiences a magnetic Lorentz force because of which it describes a circular path. And the force experienced by the charged particle can be given by the expression in the vector form f vector equals q into v vector cross b vector. If the charged particle is negative, then we can have a negative sign over here. What will be the difference between the movement of these two charged particles? Both the charged particles plus q as well as minus q will describe a circular path. But there is a marking difference. If the charged particle plus q is moving in the uniform magnetic field, if I consider with the help of Fleming's right-hand rule also, you can determine the direction, or else you can go with the vector cross product. With that also you can determine the direction of the magnetic field. So we can say here, if the charged particle is moving with a velocity v here, magnetic field is b. So this is the direction of rotation, v vector towards b vector, so force will be acting outwards. So what will happen? The charged particle will be describing a circular path like this. So it will be coming out of the plane of the board and will be describing a circular path like this. If a negative charge is moving in the same magnetic field b vector, then what will happen? It will be describing a circular path in the opposite direction. So you should remember in what direction the charged particle is moving, because in all the cases the problem, while discussing problem in Lorentz force, this is very important. Depending upon the nature of the charge, the direction of force changes. If charge has a positive sign, force will be acting in one direction. If the charge gets a negative sign, then the force will be acting in the opposite direction. So F vector equals minus of q into v vector cross b vector if the charge is negative. If the charge is positive, then F vector equals q into v vector cross b vector. So once again I would like to say, if charge is moving with a velocity v in the direction of in the perpendicular direction to the uniform magnetic field, then the charged particle will describe a circular path like this, because the force is acting outwards. So it will pull the charge outwards. So at each and every point the force is acting perpendicular to the velocity, so it will be changing its direction. If it is negative charge, then opposite is the direction of motion of the charged particle. Based on this formula, we are going to discuss a problem from which we are going to obtain certain important results, which are very important. Let us see the problem here. A particle of charge q moves with a velocity v vector along the positive y direction. So this is the direction x, y, and then z. This is the direction in which the charged particle plus q is moving, and it is the velocity v. So v vector is acting along y direction. And then in a magnetic field b vector, compute the Lorentz force experienced by the particle. First case is A, when the magnetic field is along the positive direction. If B is along the positive y direction. B is along the positive y direction. And the second one, when the magnetic field is points in the positive z direction. The magnetic field is pointing in the positive z direction. And the third case is that when the magnetic field is in the zy plane, magnetic field is in the zy plane, he is making an angle theta with the velocity of the charged particle. Mark the direction of the magnetic force in each case. You are asked to calculate or mark the direction of the magnetic force in each case. You just look at the diagram here. This is the diagram for the first case. What is mentioned here? Charged particle plus q is moving with a velocity in the positive y direction, and the magnetic field is also moving along or acting along the positive y direction. So b vector is also acting along the positive y direction. So in the vector form, I can say velocity of the charged particle. Velocity of the charged particle is given by V vector is equal to V into j cap. Magnitude multiplied by direction. Magnetic field B of the magnetic field B acting is given by B vector equals P into j cap. What is asked? We are asked to calculate the magnetic Lorentz force as well as we are asked to mention its direction. Magnetic Lorentz force is Fm, or simply I can mark F vector is equal to Q into V vector cross B vector. So this is Q into V vector is Vj cap cross B vector is Bj cap. From vector rules we can say J cross J is 0, so the entire term goes 0. So the magnetic Lorentz force is 0. So what do you understand from this? This is the very first result. When the charged particle moves parallel to the magnetic field, when a charged particle moves parallel to magnetic field, the magnetic Lorentz force experienced by the charged particle is 0, or else you can say no magnetic Lorentz force acts on the charged particle. So the magnetic Lorentz force Fm is 0 when the charged particle moves parallel to or anti-parallel to the magnetic field. Just look at the case here. If magnetic field is acting along the same direction, if the charge reverses this direction, if it is said to move in the negative y direction, then also there will be a minus sign over here. Once again J cross J will become 0, force will be 0. So this is the very first result actually. Generally, while solving problems, you should not look at the numericals. You must look at the concept. Here, we are getting the first result that the force acting on the charged particle is 0 when the charged particle moves parallel to or anti-parallel to the magnetic field. First case. Second case is when the magnetic field acts along the positive z direction. What will be the case? You can just draw the diagram here. Magnetic field is acting along the positive z direction. B vector is acting along positive z direction. Then what will be the case? Velocity of the charged particle is once again mentioned as V vector equals Vj cap. Magnetic field is B vector is equal to, I can change this one, B vector is equal to B into k cap, because field is acting along the z direction. Unit vector corresponding to the z coordinate is k cap, so B into k cap. Magnetic Lorentz force is F vector equals Q into V vector cross B vector, so this will become B into k cap. As you know very well, I, J and k cap. When you take the cross products, I cross J is k cross I is J, and J cross k is I. We are having J cross k. So the result is I cap. So what will be the magnetic Lorentz force here? F vector equals QVB into I cap. So the magnitude of the magnetic Lorentz force is simply QVB, and the direction is along the positive x direction or I cap. Positive x direction or I cap. So F vector equals QVB into I cap. So what is the conclusion to which you can arrive at? So when a charged particle moves perpendicular to a uniform magnetic field, when a charged particle moves perpendicular to a uniform magnetic field, the force experienced by the charged particle is maximum and is equal to BQV. And it is equal to BQV. What is the direction in which the magnetic Lorentz force acts? As I told you earlier, V vector towards B vector, if I rotate it through the smallest angle, force is represented by the thumb, which will be acting perpendicular to the plane of the board outwards. So I can say force will be acting outwards along the positive x direction. Outward directions can be represented with a circle marked with a dot. In the previous section I told you a circle with a dot represents the outward direction and a circle with a cross represents the inward direction. So this is the second case. So when a charged particle moves perpendicular to the uniform magnetic field, it will experience a force which is given by the expression F is equal to BQV. This is maximum, and it acts perpendicular to the plane containing V vector and B vector. Simple. And then the third case is the magnetic field is acting in the ZY plane, making an angle theta with the velocity V vector. So this diagram must be changed for the third case. B vector is making an angle theta with V vector. Then what is the magnitude of the magnetic Lorentz force and what is its direction? Just look at the case once again. Velocity of the charge of the particle is the same as it is Vj, but B is making an angle theta with V vector. So B must be resolved into two components, rectangular components. So if B is acting by making an angle theta, then I can resolve it into two components. One is B cos theta and another one is B sin theta. This is the representation in terms of magnitude. Along with the direction, I can write here B cos theta j cap and B sin theta k cap. So these are the two rectangular components of the magnetic field B vector. So B vector must be represented as, I am changing this, B vector must be represented as B vector is equal to B cos theta j cap plus B sin theta k cap. These are the two components of this magnetic field now. What is the magnetic Lorentz force here? F vector is equal to Q into V vector cross B vector. So V vector is Vj cap cross B vector is B cos theta j cap plus B sin theta k cap. And as you know very well, the cross product of j cross j is 0, so this cross product goes off. And then cross product of these two, j cross k is I, so you will have BQV sin theta into I cap. BQV sin theta into I cap. So if a charged particle is moving by making some angle theta with the magnetic field, or magnetic field is making some angle theta with the direction of motion of the charged particle, then the force acting on the charged particle is given by F is equal to BQV sin theta. If theta is some 45 degree, what is sin 45? 1 by root 2. So force will be equal to BQV by root 2. If it is making an angle of 30 degree with respect to the magnetic field, or magnetic field is making an angle of 30 degree with respect to velocity, then half of BQV. What is the direction? Once again, force acts perpendicular to the plane of the board outwards. Force acts perpendicular to the plane of the board outwards. So you just look at the case here, BQV sin theta. If I represent this in vector form, once again I can write Q into V vector cross B vector. Q into V vector cross B vector. And what is the direction? Direction is along the direction of I cap, unit vector, along the x direction. So force F vector is equal to BQV sin theta into I cap. So we can simply say, when a charged particle, we can conclude, when a charged particle moves parallel to or anti-parallel to magnetic field, this is the first result. When a charged particle moves parallel to or anti-parallel to magnetic field, the force experienced by the charged particle is 0. Already you might have studied that the force acting on a charged particle which is at rest is also 0, because velocity term is 0, V is 0. V is 0, so force acting on the charged particle is 0. That is the second result. Third result is that if the charged particle moves normal to the magnetic field, then the force experienced by the charged particle is maximum, which is BQV. And the direction, as you know, depending upon the direction of velocity in the magnetic field, you can speak about the direction of force. And the next one is when the charged particle moves by making some angle theta with the magnetic field, or magnetic field makes some angle theta with the direction of motion of the charged particle, then the force experienced by the charged particle is given by BQV sin theta. Depending upon the value of theta, the magnitude of force changes. But what about the direction? Once again, the direction acts perpendicular to the plane of the board containing V vector and B vector. That's all about this problem. Then we shall go on to the next problem. Example 3.21. Compute the work done. Compute the work done and the power delivered by the Lorentz force on the particle of charge Q moving with the velocity V vector. Calculate the angle between Lorentz force and velocity of the charged particle and interpret the results. So, we shall see the next problem here. Example 3.21. Example 3.21. Compute the work done and power delivered by the Lorentz force on the particle of charge Q and velocity V. Calculate the angle between the Lorentz force. They are asking you to calculate the angle between the Lorentz force and the velocity of the charged particle, and also interpret the result. Angle between force and the Lorentz force and velocity. They are asking you to calculate the angle between the Lorentz force and velocity. So the question is very simple. What is the amount of work done by the magnetic Lorentz force when the charged particle Q is moving with the velocity v? Listen to the question. The charged particle Q is moving with the velocity v in a given magnetic field. What is the amount of work done? That's the first question. So, in order to calculate that, the magnetic Lorentz force F vector is equal to Q into V vector cross B vector. This is the magnetic Lorentz force which will be acting on the charged particle when it moves in a uniform magnetic field with the velocity B vector. What is the amount of work done? As you know very well, work done is equal to force into displacement. So, for smaller amounts, we can write the dr, F vector dot dr. As a whole, to calculate the total work done, I can write F vector dot dr vector. So F vector is nothing but Q into V vector cross B vector, and dr vector is nothing but V vector dot dt or V vector into dt. Since velocity equals displacement divided by time. So Q into V vector cross B vector dot V vector dot d vector or V vector into d vector. So there is a dot product. So V vector cross B vector. What is the resultant vector for this V vector cross B vector? Force vector. As you know very well, this is a cross product which will give you the force vector. So F vector dot d vector. F vector dot d vector. In the previous problem, we saw the force acts perpendicular to plane containing V vector and B vector. Force is acting perpendicular. Velocity perpendicular to the velocity vector. So force vector and velocity vector are at right angles to each other. The two are orthogonal. If the two are orthogonal, then the dot product of the two vectors will be equal to 0. So the entire term goes 0. So the work done by the magnetic Lorentz force on the charged particle moving with the velocity v in a given magnetic field or in a uniform magnetic field is 0. So no work is said to be done on the charged particle. And then what is the next thing asked? You are asked to calculate the power delivered. What is the power delivered on the charged particle? As you know very well, rate of doing work is power. dW divided by dt is equal to power. This is also 0. As work done is 0, power delivered is also 0. As work done is 0, power delivered is also 0. And then third one, what is the angle between the force vector, magnetic Lorentz force vector and velocity vector? You can just look at the case here. F vector, actually V vector cross B vector is nothing but the force vector, magnetic Lorentz force, dot V vector. And this force and velocity vector are mutually orthogonal. They are at right angles to each other. So F vector is acting perpendicular to V vector. So for that question, the angle theta between force vector and velocity vector is 90 degree. Force acts perpendicular to velocity vector. Then, what will be the result of this F vector dot d vector? As we mentioned earlier, that is equal to 0. So the magnetic Lorentz force does not do any work. Shall we say that there is no force acting on the charged particle? No. Force is acting on the charged particle, moving with the velocity v in the uniform magnetic field. But it changes only the direction of the motion of the charged particle, and the magnitude of velocity remains unchanged. Magnitude of velocity remains unchanged. So the magnitude of velocity of the charged particle do not change. Only the direction of motion of the charged particle alone changes, because force acts perpendicular to the velocity. Force is orthogonal to V vector. And also there is no change in the kinetic energy. Also in the previous session you had a discussion with the motion of a charged particle in a uniform magnetic field, where you would have obtained certain results which describes the motion of the charged particle. As we got the result here, motion of charged particle in uniform magnetic field. As we know, When a charged particle moves normal to uniform magnetic field, it experiences a magnetic Lorentz force because of which it describes a circular path. If a charged particle describes a circular path, then it should possess certain radius. And the radius of the charged particle is obtained as mv divided by b cube. This is the expression for the radius of the charged particle. This has been obtained using this centripetal force. The magnetic Lorentz force provides the necessary centripetal force for the charged particle to describe a circular path, whose radius is obtained as r equals mv divided by bq. This is one result. If a charged particle describes a circular path, then it should possess certain amount of radius that is obtained with this expression. Also, it should possess certain time period to complete one circular path. So, the time period of rotation or revolution of the charged particle in a uniform magnetic field is given by t equals 2 pi m divided by b cube. 2 pi m divided by b cube. Then, if time period is known, then you should know about the frequency of the charged particle with which the charged particle describes a circular path. As you know, frequency is the reciprocal of time period, so you will have b cube divided by 2 pi m. F is equal to b cube divided by 2 pi m. If frequency is known, then we have to calculate angular frequency. Angular frequency omega is equal to 2 pi f. Omega is equal to 2 pi f. This is equal to bq divided by m. Now, you might have got the name for these two frequencies. This frequency is called gyro frequency or cyclotron frequency. Gyro frequency or cyclotron frequency. And then, look at these expressions, time period and frequency. This time period and frequency depends upon, I can just do it here, t equals 2 pi m divided by bq. I can rewrite the expression as t equals 2 pi m or 2 pi divided by b into q divided by m. What is this q by m? We call it specific charge. Charge per unit mass. Specific charge. Similarly, for frequency, you can write b divided by 2 pi into q divided by m. So, what we can conclude from these expressions is that the time period and the frequency of the charged particle depends upon the specific charge of the charged particle and not on the velocity and the radius of the charged particle. So, time period and frequencies are independent of velocity and radius. This is the important result. Time period t and f are independent of velocity and radius, and it depends upon, and time period and frequency depends upon, t and f depends upon specific charge. Depends upon specific charge q divided by m. As you know very well, the specific charge of different particles differ. If the specific charge differs, then the time period of revolution of the charged particles and frequency of rotation of the charged particle will also differ. If you consider an electron, then specific charge is more. Specific charge is more, so time period is less for the electron. And the frequency of rotation is more for the electron. In the same way, you can discuss for any number of charged particles if you know the values of the specific charges of the respective charged particles. Now, if the same charged particle, if this is the condition for the movement of a charged particle perpendicular to the uniform magnetic field. A charged particle Q moving with a velocity v in the uniform magnetic field. For this orthogonal condition, for this perpendicular condition, you are obtaining these results. R equals mv divided by bq, t equals 2 pi m by bq, f is equal to bq divided by 2 pi m, and omega equals bq divided by m. Important results. And we are concluding that time period and frequency are independent of velocity and radius and depends upon the specific charge of the charged particle. Fine. Now, if the charged particle moves by making some angle theta with the magnetic field, then what will be the case? What is the path followed by the charged particle? Will it describe a circular path or otherwise any other path? That is important here. So, if if a charged particle q, let us consider a plus q, is moving with a velocity v by making an angle theta with the uniform magnetic field. Uniform magnetic field is B. Charged particle is moving with a velocity v by making an angle theta with the magnetic field. Then we can simply say here the velocity of the charged particle can be resolved into two components. I can take this as two rectangular components. One is v1 equals v cos theta and another one v2 equals v sin theta. So I am getting two components of this velocity v. One is the horizontal component, v1 is equal to v cos theta. It acts parallel to the magnetic field B. v2 equals v sin theta. This acts perpendicular to the magnetic field B. The v sin theta component acts perpendicular to the magnetic field B. What is the role of this v sin theta and v cos theta? This v sin theta component of this velocity makes the charged particle to describe a circular path. That provides the necessary force to describe a circular path. So v sin theta component makes the charged particle to describe a circular path. V cos theta component is acting along the direction of the magnetic field, so it makes the charged particle to move linearly. So what you can say is the charged particle q moving with the velocity v by making an angle theta with the magnetic field possess two types of motion. One is linear motion and another one is circular motion. Linear motion is provided by the cos theta component of velocity. Circular motion is provided by the sin theta component of velocity. So, consequently, we can conclude that the charged particle possesses both circular as well as linear motion. If the two are acting simultaneously, if the two movements are acting simultaneously, then what will be the result? A charged particle is describing a circular path. You just listen to the movement of my hand. The charged particle is describing a circular path. If it is acted upon by a force linearly, then what will be the case? I am pushing my hand along the linear direction also. At the same time, it is undergoing a circular motion. So what will be the final result? Look at the case here. This is describing a circular motion and my hand is pushing it. You just look at the case. My hand is pushing it. So linear movement is also taking place, circular motion is also taking place. The result is a helical path. So, consequently, the path of the particle will be helix. As you know, you might have studied in biology, dual standard DNA structure, helical structure. And you might have seen near the overhead tanks, you might have seen a spiral shaped ladder. That is also a helical structure. When you sharpen your pencil, then the wooden specks will be just coming out as a spiral. That is also helix. So we can just go on with so many number of examples. So what is the path followed by the charged particle? Just look at the case here. When the vertical component is making the charged particle describe a circular path, and this cos theta component, horizontal component, is making the particle to describe a linear path. If these two are acting simultaneously, they are not acting one by one, they are acting simultaneously on the charged particle. That's the reason why the charged particle describes a helical path. So, particle will be moving initially with the velocity v along this direction, making an angle theta with the direction, but it changes the direction. This is how it spirals out. This is how the charged particle will be moving. So, in this particular case, the sin theta component maintains the parameters of a circular path, and this cos theta component is used to calculate the pitch of the helix. What is the role of the sin theta component? Once again, I could say, see, this sin theta component acts perpendicular to B. It provides the circular motion for the charged particle. Also, it maintains the parameters of circular path. Parameters of circular path. What about this cos theta component? It acts parallel to magnetic field. It makes the charged particle to move linearly, and also it is used to calculate the pitch of helix. Very important. Pitch of helix. So sin theta component determines the parameters of the circular path. Cos theta component determines the pitch of the helix. What is pitch of helix? It is the linear distance traveled by the charged particle when the charged particle completes one circular revolution. You can just consider here. If the charged particle starts from here and it completes one revolution and reaching the same point but shifted through some distance. And the distance traveled horizontally. Or linearly. Distance traveled linearly. When the charged particle describes one circular revolution is called the pitch. That is called the pitch of the helix. Or otherwise, in other words also we can say the pitch of the helix is the linear distance covered by the charged particle. Linear distance covered by the charged particle when the particle completes a revolution in a time period t. What is capital T? You have marking difference between small t, capital T. Small t refers to a time duration. Capital T refers to time period. Time period in the sense it is the time taken for one complete revolution. Time taken for one complete rotation. That is specified by capital T. What is small t then? If 10 rotations are made, what is the time taken? That will be measured with the help of small t. So, it is the linear distance traveled by the charged particle in a time period of t, in a time period capital T. So in a time period capital T, the distance traveled, linear distance traveled by the charged particle is given by the term called pitch of the helix. So if a helical path is carried out, then what is the radius of the charged particle possessed by the radius of the charged particle? What is the time period? What is the frequency? What is the angular velocity? And then finally, what is the measure of pitch? This you have to calculate. So, we shall calculate the radius here. R equals mv divided by bq is the expression, and charged particle moves perpendicular to the magnetic field. But here, we have a helical path. Also, we had an idea that the charged particle describes a circular path, and the parameters of the circular path is determined by the velocity v2, which is v sin theta. So the expression must be replaced as mv2 divided by bq. mv2 divided by bq. R equals mv2 divided by bq. How come this is coming? q v2 b equals mv2 square divided by r. From this expression, v2 gets cancels out. R equals mv2 divided by bq. Also, I can write mv sin theta divided by bq. The radius of the circular path is determined by theta also. R equals mv divided by bq. This will give you the radius of the charged particle describing a helical path. Then what is the time period here? As you know, time period is given by the expression t equals 2 pi r divided by v2. T equals 2 pi r divided by v2. What is r here? Otherwise I can write 2 pi divided by v2 into r is mv2 divided by bq. v2 gets cancels out. So you will get the result 2 pi m divided by bq. Look at the expression. The time period for the charged particle describing a circular path when it moves perpendicular to the magnetic field is also 2 pi m by bq. When it is possessing a helical path, then also it is t equals 2 pi m by bq. Then frequency we can calculate. It is reciprocal of time period. This is bq divided by 2 pi m. What is the angular frequency? Omega, that is equal to bq divided by m. bq divided by m. So if you look at the expressions, only the radius is changing. This is for helical path. I can compare. This is for circular path. In circular path, r is simply mv divided by bq. This is mv sin theta by bq. Time period is same, 2 pi m by bq. Frequency is same, bq divided by 2 pi m. And then angular frequency is also same, bq divided by m. So the only difference is with the radius, r equals mv sin theta divided by bq. Now we have to calculate the pitch of the helix. Pitch of the helix can also be expressed very simply here. Just go here. Pitch of the helix is the horizontal distance or linear distance traveled. So pitch is nothing but distance traveled. Distance is velocity into time. What is the velocity in the horizontal direction? V1 into time period is capital T. Time period is capital T. Simple. What is the velocity here? V1 is nothing but V cos theta. What is the time period? T equals 2 pi m divided by bq. So the pitch of the helix is given by the expression d equals 2 pi m by bq into v cos theta. Pitch of the helix d equals 2 pi m by bq into v cos theta. This is the pitch of the helix. So these expressions are very important. When a particle is describing a circular path, that is different. When a particle is moving with a velocity v by making some angle theta with the magnetic field, then the particle describes a helical path. You must be clear. You have to read out the question carefully. Particle moves perpendicular to the magnetic field, describes a circular path. Particle moves with a velocity v by making an angle theta with the magnetic field, then the particle describes a helical path. If helical path is considered, then the radius of the charged particle is mv sin theta by bq, not mv by bq. mv sin theta by bq. And the pitch of the helix is given by the expression d equals 2 pi m by bq into v cos theta, which is nothing but the product of velocity and time period. That's all. V1 into capital T. V cos theta into 2 pi m by bq. So d equals 2 pi m by bq into v cos theta. This is about the pitch of the helix. Fine. We shall see an example corresponding to this one. Before speaking about that, is this real when a charged particle moves by making some angle theta with the magnetic field? Will it describe a helical path? Of course, yes. And this was studied with the help of a particle detector. When an electron was allowed to move through the particle detector called a cloud chamber, there with the condensation of water droplets, the path of the electron beam has been studied, and it was found that our electron has been studied, and it was found that the electron carried out a helical path. That is experimental observation for the movement of the charged particle when moves with respect to a magnetic field by making some angle theta. Then it is very clear that it describes a helical path. Now we can see the example corresponding to this movement of charged particle. Example 3.23. A proton moves in a uniform magnetic field of strength 0.5 Tesla, is directed along the positive x-axis, so I can mark it as I cap. At the initial time t equals 0 second, the proton has a velocity v vector is equal to 1.95 into 10 power 5 I cap plus 2.00 into 10 power 5 k cap meter per second. Find at initial time what is the acceleration of the proton. First question is, what is the acceleration of the proton? And the second question is the path circular or helical? Is the path circular or helical? If helical, calculate the radius of the trajectory and also calculate the pitch of the helix. If it is helical path, then calculate the radius and pitch of the helix. As you know, pitch of the helix is the distance traveled by the helix axis per revolution. Right, data are given. Sorry. A proton is moving. As it is mentioned, with a proton, the charge of a proton is 1.60 into 10 power minus 19 coulomb. This is important to calculate the required data. If acceleration is required, then we should know about the value of magnetic Lorentz force. So 1. Magnetic Lorentz force can be calculated. F vector equals Q into V vector cross B vector. Charge of the proton is 1.60 into 10 power minus 19 into velocity of the charged particle is 1.95 into 10 power 5 I cap plus 2.00 into 10 power 5 k cap cross B vector is 0.5 I cap. 0.5 I cap. So I cross I is 0. K cross I is J. K cross I is J. As I showed you the vector determination of the unit vectors, cross product of unit vectors, we can say K cross I is J. So this cross product is 0 and this product will be giving you a result in the J direction. So I can have 1.6 into 10 power minus 19 into 2 into 0.5 is 1. So into 10 power 1 into 10 power 5, K cross I is J cap. So this is 10 power minus 14. So 1.6 into 10 power minus 14 J cap is the force experienced by the proton, and it is said to move in the uniform magnetic field with the velocity 1.95 10 power 5 I cap plus 2.00 10 power 5 K cap. Now, if force is known, you can easily calculate the acceleration as per Newton's second law. A equals F vector divided by M. F vector is 1.6 into 10 power minus 14. J cap is there, so in order to mention the direction, I can have J cap. And what is the mass of proton? Mass of the proton is 1.67 into 10 power minus 27 kilogram. So mass of proton is 1.67 into 10 power minus 27 kilogram. So I am substituting that. So if you calculate the value of acceleration, you will have a result which is 9.58 12 meter per second square. So the acceleration of the charged particle is 9.58 in 10 power 12 meter per second square J cap. So once again, we can say here acceleration takes place along the direction of the force. Acceleration takes place along the direction of force. If force is acting along the J direction, acceleration will also take place along the J direction. Its value is 9.58 in 10 power 12 meter per second square. Now, the second question is, what is the path of the charged particle, whether it is circular or helical? If helical, then find out the radius and the pitch. As you know, if a charged particle is moving with these two components, two velocity components, then definitely the charged particle is moving by making some angle theta with the magnetic field. So the path followed by the charged particle is helix. So we can do it here. Force is here, acceleration whose value is also here. So we can just mark it. F vector equals 1.6 into 10 power minus 14 J cap. Acceleration is asked, which is 9.58 into 10 power 12 meter per second square J cap. Then what is asked? What is the path followed by the charged particle when the velocity components are given? We can say the path followed is helical. If path followed is helical, then what is the radius? R equals mv sin theta divided by bq. Or otherwise I can write mv2 divided by bq. mv2 divided by bq. Just look at the case here. Velocity component is given 1.95 into 10 power 5 I cap and 2 into 10 power 5 K cap. So one is along the x direction and another one is along the z direction. So V2, vertical component is required, which is this one. This is V2 and this one is V1. So V2 is 2 into 10 power 5 K cap. So radius can be calculated as R equals mass of the proton is 1.67 into 10 power minus 27 kilogram into V2 is 2 into 10 power 5 divided by magnetic field is given 0.5 Tesla and the charge is 1.6 into 10 power minus 19. So what will you get? Approximately or close to this value, you will get 4.2 millimeter. The radius of the charged particle is 4.2 millimeter. If you calculate this 1 by 2, so you will get 4. This is 0.4. If you cancel out this is 0.4. 1.67 divided by 0.4. Hardly you will get 4.18 something. So I am rounding it off to 4.2 millimeter. The radius of the circular path described or the circular motion described by the charged particle is 4.2 millimeter. So radius was asked. So we found the value of radius 4.2 millimeter. Then they are asking you to calculate the pitch. In order to calculate the pitch, we need two velocities, one v1 and another one the time period. V1 is there in the data itself. We need to know the value of time period. Time period is T equals 2 pi m by BQ. Substitution is 2 into 3.14 into 1.67 into 10 power minus 27 divided by magnetic field is 0.5 and charge is 1.6 into 10 power minus 19. 1.6 into 10 power minus 19. And the value of the time period. The value of the time period is found to be 13.1 into 10 power minus 8 second. Time period is T equals 13.1 into 10 power minus 8 second. 13.1 into 10 power minus 8 seconds. So time period is calculated. T equals 13.1 into 10 power minus 8 second. Then finally you can calculate the value of pitch. Pitch D equals velocity V1 into time period. V1 is from the expression 1.95 into 10 power 5 multiplied by time period is 13.1 into 10 power minus 8. This will be around 25.5 millimeter, which is 25.5 millimeter. So if you look at the case, since the electron possesses certain amount of acceleration, proton possesses certain amount of acceleration, the pitch of the helix is almost 6 times that of the radius of the helix. Look at the radius here. Radius is 4.2 millimeter. Pitch of the helix is 25.5 millimeter. So what will happen? Radius is 4 millimeter and the pitch of the helix, actually as it describes a helical path, this distance is 25.5 millimeter. So when compared to the radius, this is around 6 times. 6 times. So as per the question, as per the data, we are very clear. What will happen if a charged particle is moving with a velocity with these components in a magnetic field of 0.5 Tesla? What is the initial acceleration when time period t equals 0? For that case, we have to calculate force. Force whose magnitude is obtained as 1.6 in 10 power minus 14 J cap. Acceleration is obtained as 9.58 in 10 power 12 meter per second square. As I am running out of time, I just gave you the results directly. You can simply calculate. For calculation purposes, it will take hardly some 2 minutes extra. You just do it. Acceleration is 9.5 in 10 power 12 meter per second square. And then second question is, what will be the path followed by the charged particle, whether it is circular or helical? As there are components of velocities, definitely the path followed by the charged particle is helix. So helical path is carried out. Radius of the charged particle is mv2 divided by bq. Velocity is given 2 into 10 power 5 k cap. So on substituting the velocity, you need to find out which one is v1 and which one is v2. This is horizontal velocity and this one is vertical velocity. The vertical velocity component determines the parameters of the circular path. So r equals 4.2 millimeter. Radius is determined. In order to calculate pitch, time period should be known. Time period is not asked, but it is required to calculate the pitch v1 into t. So time period is 2 pi m by bq. There is no change in the formula for helical path as well as circular path. So time period is 13.1 in 10 power minus 8 second. With this time period, with this velocity, the pitch travelled by the charged particle, that is the linear distance covered by the charged particle in one complete revolution. Definition for pitch is this one. Linear distance travelled by the charged particle in one complete revolution is v1 into t, which is 1.95 in 10 power 5. This is the velocity v1. And the time period is this one. You will get 25.5 millimeters. So to conclude, why pitch is much more when compared to radius? Because the proton possesses an acceleration. Because it is accelerated, so it will be spiraling forward. So the pitch is 6 times greater than that of the radius of the circular path. Thank you.